When a molecule has two carboxylic acid functional groups in it, and those groups are not close to each other, they each behave about like you would predict based on the chemistry you know for monocarboxylic acids. But when those carboxylic acid functional groups get to be close together, the molecule has special chemistry that we ought to talk a little bit about. First, look at the effect on the strength of the carboxylic acid. For comparison, I'm going to put the pKa of acetic acid up here. In oxalic acid, the carbonyl groups are attached to each other. And the electronic effect of one has a strong effect on the pKa of the other. Let me just pick this one and show the partial positive charge on carbon, which helps stabilize the anion in the carboxylate, making this a stronger acid. pKa is 1.2. This is more than 3,000 times as acidic as acetic acid. Malonic acid has a methylene group separating the two carboxyl groups. They still have the same electronic effect, but it's not as great. The pKa is about 2.8, which makes it about 100 times more acidic than acetic acid. And once you put two methylene groups in between those two, the effect is even much smaller. This is succinic acid. pKa is 4.2. Now it's about 3 times as strong as acetic acid, not so much of a difference. So when the carboxyl groups are really close, there's a strong acidifying effect. As they are separated by more methylene groups, that effect is attenuated. It's what you would expect. There's an interesting reaction when the carboxyl groups are separated by 2 or 3 methylene groups. I'm going to rewrite this structure. I'm going to put the 2 methylene groups just like this, and write the carboxyl groups in this conformation, just to make it clear what's happening chemically. When this molecule is heated, it loses 1 molecule of water to make a cyclic structure, and the driving force for this reaction is the removal of water. So very good yields of the cyclic anhydride are obtained. This is the 4-carbon carboxylic acid. Here are the 4 carbons. And now the 2 carboxyl groups are attached by sharing an oxygen. This type of molecule, where 2 carboxylic acid functionalities share 1 oxygen, is called an anhydride. And in this case, of course, it's a cyclic anhydride. Formation of 5-membered rings is favorable, and the formation of 6-membered rings also is favorable. So when the carboxyl groups are separated by 3 methylene groups, this also works well. I'll rewrite the structure. We have 3 methylene groups between the 2 carboxyl groups. So we need to draw 3 methylene groups in this conformation. Here's the 3rd. We'll draw the carboxyl group here, and when it's heated, water is lost to form a 6-membered ring. You share the oxygen here. So these 2 special dicarboxylic acids form cyclic anhydrides readily. And there's one more special reaction to talk about. Malonic acid undergoes decarboxylation when it's heated. Looking carefully at this reaction, you see that a carboxyl group has been replaced by a hydrogen. Let me put those in a special color. Of course, normally we would write this product as acetic acid, CH3CO2. This is a pretty remarkable transformation. Using arrow pushing in the following mechanism, we can understand how this happens. A pair of the pi electrons in this carbonyl group can be used to form a bond with hydrogen. And this pair of electrons moves to form a double bond with this carbon, which is lost as CO2 while this bond breaks to form a new double bond. This is a cyclic movement of 3 pairs of electrons, which all happen simultaneously and in an equilibrium that strongly favors formation of carbonyl. A base removes this proton, and an acid protonates the double bond. So we have the carboxylic acid structure I've shown above. And I show one of these protons in blue so we can see it came from this acid. So this is a special reaction of malonic acids, not other dicarboxylic acids. They decarboxylate, losing a carbon and replacing it with a hydrogen. The products are acetic acid, or substituted acetic acids. Later you'll see that this is important both in organic synthesis and in biosynthesis. In biological chemistry, this is especially important. It builds large molecules from a small molecule, 2 carbons at a time.